So my name is Pankaj Mishra from IIT Guwahati, and it's my privilege to session this chair. So in this session, we'll have the two talk. The one given by Professor Mishkatul Bhattacharya, and another one will be from Jubin Jacob. So Mishkatul is from Rochester Institute of Technology, and his main research interests are theoretical quantum optics, optomechanics, optical tweezer, and nanoparticle, Bose-Einstein Condensate. And today he'll be talking on cavity optomechanical sensing and manipulation of an atomic persistent current. So Muscat, you will have 45 minutes. So 35 for talk, 10 minutes for questions.
Okay, great. Thank you very much. Pawan, can you hear me? Yes. Okay, excellent. Good morning and welcome to the first talk of the day. So as Pankaj very nicely and very kindly introduced me, that's my name. From the Rochester Institute of Technology. I will have a more detailed slide with the collaborators. So this is, we have a quantum optics theory group, and we are mostly focused on light matter interactions. These are some of the topics we're working on. This is the campus in the high and low temperature regimes. As you can see, I have a moderately long list of collaborators, but I'm always looking for more. So if there is any overlapping topic and I have not yet approached you, please come and find me. I would love to learn from what you're doing and maybe even do something together. The physics department at my institution does not have a PhD program, so I don't have any graduate students. I mostly work with postdocs and undergraduate students. And in fact, a large number of those postdocs come from India. Pardeep, who is the lead author on the topic that I will present today, came to us from IIT Ropar. He's Shubhrangshu's graduate student. Sandeep came from Tarak's group, Kani from Harsha Vanare's group at IIT Kanpur, Arpita from Professor Bimalendu Dev's group at Cultivation, and so on. So I'm actually currently looking to hire postdocs. So I've put my email there. If you're interested, please send me an email and we can take it from there. So here's a quick outline of the talk. I will first introduce atomic superfluid rotation and then move on to cavity optomechanics. And these are actually two very substantial but quite separate fields of research at the frontier of physics today. And our attempt is to kind of bring them together in a fruitful way. And the specific problem we'll be looking at is that of sensing the rotation of this atomic superfluid. But by the time I end, I hope to convince you that there are many more things that can be done using this combination. So just to remind you, the first kind of superfluidity to be discovered was superconductivity, which can be thought of as a kind of charged superfluidity by Camerlingonis in 1911. And those observations, as well as the ones that followed, were explained quite nicely by the famous theory of Bardeen, Cooper, and Schrieffer. But in 1986, and since then, a number of superconductors have been found which don't follow the VCS theory, and theory of high temperature superconductivity is one of the outstanding questions in all of physics today. In the meantime, superfluidity was identified in liquid helium, first in the bosonic and then in the fermionic isotopes. But today I will focus mostly on atomic Bose-Einstein condensates, which were experimentally achieved in 1995 and which give a very, very amazingly flexible experimental platform on which to explore the details of superfluid behavior and are also amenable to reasonably simple theories. Just to mention, there are many other systems in which superfluid behavior has been seen. So for the purpose of this talk, and I think Pankaj showed this slide yesterday, so I'll just run through it. For the purpose of this talk, BEC will be considered to be a manifestation of the wave nature of matter. So at room temperature, the particles in this hall are basically well described as billiard balls. But as we lower the temperature, the de Broglie wavelength associated with each atom increases and eventually becomes comparable to the interparticle spacing. So that's said to be the critical temperature for Bose-Einstein condensation. We have some BEC experts in the audience, so please don't hesitate to correct me if I say something wrong. And far below the critical temperature, basically all the atoms become indistinguishable. We have a giant matter wave where all the atoms are represented, each atom is represented by a wave which is indistinguishable from the others. Now, in his original proposal, Einstein considered non-interacting atoms. So in this talk, I will consider weakly repelling atoms, because that's what we see in the experiments that are relevant to our work. For the rest of the talk, this is going to be useful, so I will quickly run through how atoms in the BEC interact with various kinds of electromagnetic fields. This is probably all known to you, so I'll make it quick. The critical temperatures are typically hundreds of nanokelvin, so they are too low for any material container to contain these condensates. So they have to be levitated in space, basically using electromagnetic containers. So a popular trap is a magnetic trap, and the most popular magnetic trap is the harmonic magnetic trap, which is simply connected. But for this talk, the focus will be on this multiply connected ring or toroidal geometry. And I would also like to mention how light interacts with these atoms. So we know if we have a laser which is sending out photons that are resonant with some transition in the atoms that make up the condensate, the atoms are going to absorb those photons. Eventually, they're going to decay back through spontaneous emission. And this is going to release a photon for each atom in a random direction. And this random recoil is going to destroy the motional coherence between the atoms. Basically, the condensate is destroyed. And the reason this is important is because all methods of measuring the condensate basically rely on some form of photograph taking, which is this absorption imaging method. You shine resonant light on the condensate and you look for a shadow on a screen. So that destroys the condensate. What if the light is off resonance, so far off resonance that the probability of the atom being excited is negligible during the experiment? Well, then we can forget about the excited state. However, the ground state still shows some non-trivial effects. For example, it undergoes this AC stock shift. Its energy is changed. So if I am thinking of an atom moving from right to left across a focused Gaussian beam, basically the ground state energy will go up and hit a maximum at the axis of the beam and then come down. And so what this means is that if we have a focused beam, we can use it to push an atom around. And in fact, if we put a Bose-Einstein condensate in a ring trap and then use a focused beam to stir optically, then we can set these atoms into motion. And what we find is that if we look at the angular momentum per atom divided by h bar, this quantity, which is sometimes called the winding number and sometimes the topological charge, as a function of the stirring rate, we find it's quantized, okay? And quantized flow is a hallmark of superfluidity. These experiments were first done in the laboratory of Bill Phillips, who received the Nobel Prize for laser cooling and trapping. And the atoms on the ring can be described very simply using a wave function, sometimes called an order parameter, which is given by the square root of the linear atom density, in this case, divided by 2 pi, and this phase factor, which involves the quantized winding number. So LP equal to 0 corresponds to a state of no rotation, LP equal to 1 unit of rotation along a certain direction, depending on your convention, and then -1 is rotation in the opposite direction, and so on and so forth. So why are these topologies interesting? Why not just stick to the harmonic traps? One nice thing about the ring trap is that by enforcing a density null at the center, it pins any kind of rotation down, okay? It restricts to the ring. So if you look, for example, to contrast it at a state of circulation excited in a simply connected harmonic trap, you see that the vortex is moving around if you follow the dark core in these images. And the ring stops that from happening. It just spins the vortex down at a certain location in space. And that's useful if you want to examine or manipulate the vortex. Another example, advantage is that you can set up quite high states of rotation here. So if you look again in a harmonically trapped BC, but now for LP equal to 2, so a doubly charged vortex, you can see that eventually it dissociates into two singly charged vortices. And this is simply because the energy of this configuration is lower than the energy of this configuration. The energy goes as the square of the angular momentum. So you can do the math and see that h bar squared plus h bar squared is smaller than the square of 2h bar, which is 4h bar squared. Again, this ring potential, if it's sufficiently tight, prevents this kind of dissociation from happening. And actually, very high states of rotation have been experimentally achieved up to 350 and then 40,000 h bar. This is the experiment of von Klitzing in Crete. And these currents persist for minutes. Okay, so like I said, LP equal to 0 corresponds to the state of no rotation. That's the ground state. And all these other states which contain non-zero angular momentum are actually excited states. They're not infinitely stable, but they're metastable. In fact, they're metastable for minutes. So anybody who is interested in a coherent system, both for fundamental and applied reasons, should sit up and take notice. Okay, I don't think you can list many qubits in whatever system you like, ions, superconducting circuits, etc., which have a coherence time that's this long. And in fact, this is limited by background pressure. So if you really have a very fancy vacuum system, I think you can do even better. So from what I have said so far, it won't come as a surprise, perhaps, if I claim that these ring condensates are paradigms of quantum rotation. They give us a localized object which we can set into a very high state of rotation and which persists for a macroscopic amount of time. So not surprisingly, this serves as a platform for many, many kinds of studies. Of course, it's a very good system for studying superfluid hydrodynamics. So phase slips, shock waves, all kinds of collective excitations, some of which you see here. The ring geometry is very nice for matter wave interferometry. You can send in atoms and then you have the two arms and then the recombination at the other end. People put semi-permeable optical barriers, and then you can mimic Josephson junctions from solid state physics. And instead of sensing magnetic fields, you can sense rotation. You can study topological defect formation, simulate the early universe. A lot of excitement has come from the last year where two groups have realized fermions in these rings and used magnetic fields and Feshbach resonances to tune these fermionic systems all the way from the so-called BCS limit to the BEC limit. So let me just say a sentence about that. In the BCS limit, the fermion pairs that are responsible for superfluidity are separated by a distance that is much larger than the interparticle spacing. And in the opposite BEC limit, where fermion pairs bind into molecules strongly to make bosons, they are separated. Now the coherence length is much shorter. It's the intermediate regime that's of great interest, because here the coherence length and the interparticle spacing are comparable, like in some high temperature superconductors like the cuprates. Actually, there are connections to quark-gluon plasma and bilayer graphene also. So this is a system that people are really, really interested in looking at. So there are many, so as you can imagine in all these experiments, the central question is, what is the state of the rotation of the condensate? What is it doing during the experiment? So there are many, many methods of measuring ring BEC rotation. By many, many, I mean 6 or 7, and that's quite a lot already, I think. And I will not talk about any of them in detail unless there are questions. But the main point is that every one of them, no matter which one you start with, requires you to do absorption imaging at the end, and so destroys the condensate. Okay. So I hope everybody in this room agrees if I say that ideally the measurement should be non-destructive, it should be in situ, and should be carried out in real time. Okay, so these are typically not in situ because the optical resolution is not good enough, so you have to switch off the trap and allow the atoms to expand via time of flight. Certainly in superconductivity and in superfluidity in liquid helium-based systems, a lot of effort has been put into making these kinds of measurements, and as a result of the success of these strategies, we have found accessible a lot of very interesting vortex dynamics in these systems. Okay, so they're very complicated, very rich. A similar effort has been undertaken for simply connected or harmonically trapped BECs, but they're really challenging experiments. Progress has been slow. So now we're asking the question that we have these ring BECs available to us. Can we construct a measurement protocol that gives us this kind of access? And there is some progress towards that from the group of Phillips that I mentioned earlier, but our proposal is substantially different. So in order to do that, I'm going to invoke possibly one of the most sensitive detection paradigms available in all of physics today, and that's called cavity optomechanics. And probably the most well-known example of cavity optomechanics is the detection of gravitational waves by LIGO, or Laser Interferometer Gravitational Wave Observatory. So here's the schematic of LIGO. It's a Michelson interferometer. So we have a laser sending light in. That's where the opto comes from. And then, of course, these mirrors form cavities where the light bounces back and forth. That's where the cavity comes from. But these mirrors are not fixed in position. They are actually suspended like pendula. So they're oscillating harmonically, and that's where the mechanics comes from. And the idea is that the gravitational wave, when it passes by, couples differently to the two arms. So there's some modulation of the path length difference, and the photodiode that's looking at the resulting intensity sees some modulation. So this is a trace of that signal over time. And according to the theory of Einstein, this chirp is due to the in-spiraling merger of two black holes many, many years ago, and they release energy when they merge, and you can see this. Now, if we convert the vertical amplitude of this signal, which is called the strain, into the displacement measurement carried out by the interferometer, so that's just given by strain times the length of the interferometer arm, then we find it's a fantastically small number. It's 10 to the minus 18 meters. That's about 1,000th of the radius of a proton, okay? So what this says is that this way of measuring motion, transducing it to optical detection, is very powerful. It's very sensitive. Of course, to be sure, LIGO is a very complicated machine. Each arm of the interferometer is 4 kilometers long. But people have taken the same physics and reduced the scale and made tabletop sensors, which are very, very cutting edge and sensitive for all kinds of physical observables, acceleration, magnetic fields, temperature, anything that you can couple, any physical variable that you can couple to the displacement of this mechanical oscillator, you can measure very well. So the basics of cavity optomechanics can be understood using a much simpler layout, optical layout than I showed for LIGO. So we just have two mirrors now. One is fixed, the other is oscillating harmonically. And a single mode of this cavity is excited by this laser. And this system was analyzed in a seminal paper by C.K. Law, who was a postdoc when I was a graduate student at Rochester. I joined in '95. And I used to see him in the hallways and wonder what he did late at night. This is what he was doing. So he wrote down a Hamiltonian which describes the system in terms of the interaction of two harmonic oscillators. One of them is electromagnetic, that's just this mode, cavity mode, and the other is mechanical, that's this mechanical oscillation. And he found that these two oscillators actually interact. And you can see that because if you think of a photon that's incident on the mirror that's oscillating, once it's reflected, its linear momentum is reversed completely. So there's a change of momentum, and that happens every time the photon comes back. So there's a rate of change of momentum per unit time. That's a force. And so as you can imagine, this force is proportional to the intensity of the light inside the cavity, or in other words, to the number of photons. So I'm writing this in second quantized notation now. And this radiation pressure force couples to the mechanical displacement of this oscillator, okay? And sometimes I like to call this the law interaction because he was really the person who set it down in very rigorous detail. Now, it is this interaction which allows LIGO to make these very, very precise measurements. But actually, LIGO is just, just the tip of the iceberg, so to speak, because there has been an enormous amount of work. Optomechanics, cavity optomechanics is a very mature field now. And using this interaction, many things can be done. There's an entire toolbox for manipulating mechanical motion. So you can carry out below quantum limit detection of mechanical motion. You can detect the back action that results from your measurement due to this protocol because of Heisenberg's uncertainty principle. You can devise means of evading that back action. You can squeeze the mechanical motion. You can cool it. You can store and retrieve optical information from mechanical. You can turn it, make it look like a laser. You can carry out entanglement, and so on and so forth. I'm actually running out of space in this slide. There is so much more to do. But the inspiration for us was, if we can engineer with our ring BEC and a cavity this kind of interaction, maybe we can take advantage of this toolbox to solve some outstanding problems in atomic superfluid rotation. So before I go ahead, and just to connect with part of this audience, which I know works on optical tweezers and nanoparticles, though it may sound quite far from the atomic physics problem I'm describing, actually you can have optomechanical systems with beams that trap nanoparticles inside the cavity. This is an optical tweezer combined with a cavity. And the physics is essentially the same because the nanoparticle works as a harmonically oscillating element. In fact, it is possible to go beyond the law interaction and remove the positive feedback provided by the cavity by just throwing away the mirrors, and instead put in some active feedback. Okay, so you have the laser, you have the focusing lens, here's the optical tweezer, you detect the displacement of the particle and then feedback using whatever transfer function you like. And then the question is, what can you do that's useful and interesting? So this is a line that we've been pursuing actually for the last 10 years in collaboration with our experimental colleague at the University of Rochester. And I apologize to Pawan because he's heard this before when I visited him in Pune. But this is also another major line of research for us. But to get back to the current problem, there is a lot of precedent for combining Bose-Einstein condensates with optical cavities. In particular, there's a pioneering experiment from Tillman-Esslinger's group who performed with an experiment that is in some sense the linear analog of what we're proposing. So they had harmonically trapped Bose-Einstein condensate, which is coupled to the standing optical lattice inside a Fabry-Perot cavity. And as a result of diffraction of the matter waves from this standing optical lattice, there is some motional or density oscillation of the condensate, and I'll describe that in detail, which allows for measurement of the condensate properties through the cavity transmission. So what we really have to do is to construct the rotational analog of this system for our ring BEC and see if that helps us. And of course, the beams that will allow us to do this, and I think somebody showed this slide, I'm not sure if it was Nirmalya or maybe Gautam Samant. So these are the familiar beams which carry orbital angular momentum. This is the Gaussian, and then this is the charge plus and minus 1. If you look at the intensity profiles, you will see they're just rings. And that should already give us a hint about coupling to the ring BEC. And if I take the +2 and the -2 and I interfere them, I get 4 maxima on a ring. And this is what we will use to set up the protocol for rotation measurement. So here's the scheme. We start with a trapped ring BEC in a cavity. There are many ways of trapping these condensates. The simplest one, possibly for our implementation, is a magnetic trap, which von Klitzing, for example, has implemented. And these are very smooth and very good at confining the atoms for a long time. And we assume that the condensate is already in motion, and it's in a rotational state with winding number LP. There are many ways of creating this rotation. One way is to simply jiggle the magnetic trap, like you rotate your lassi in your glass or your coffee in your cup. And that's what von Klitzing has done, but there are many other ways also. So I'm not going to give the details of how that rotation is set up, because our task is just to measure the system. So in order to do this, we drive the Fabry-Perot with beams carrying orbital angular momentum, plus minus LH bar. So L will be 2 for the picture that I'm showing here. That's why you see 4 maxima here. These beams will be detuned far from any atomic transition. So the condensate atoms never leave their ground state as they are rotating on the ring. However, every time they cross one of these maxima, the ground state energy will go up and down, like I showed for the light shift on my earlier slide. Okay. So what is happening here, if we take a step back, is that we have a matter wave that is going around and encountering a periodic electromagnetic structure. But we know what happens when waves encounter periodic structures. Diffraction, right? So the more familiar example is when light comes out of a laser and it encounters a material grating. So you have the undiffracted order, then you have first order diffraction and second order and so on. So here, the roles of light and matter are exchanged. Here the wave is material, the grating is electromagnetic, but the physics is the same. So what that means is that the undiffracted order corresponds to the original persistent current. And if the number of photons in the cavity is small, the lattice is weak, and then we only have to worry about first order diffraction, then there will be a small number of atoms that now have slightly higher and slightly lower angular momentum. These are the diffraction side modes set up by the atomic matter wave as it goes around and encounters this optical lattice. So once now you have 3 persistent currents going around in the ring. Of course, they will interfere with each other and they will beat, and that modulates the condensate density. And now these photons that are passing through the cavity will see this varying density and pick up phase which carries a signature of that varying density. Another way to think about this is going back to Nirmalya's slide about a spinning wave plate in the path of a beam, which gives a rotational Doppler shift. So these circulating atoms actually add a rotational Doppler shift to the photons. And by looking at the cavity transmission, we find we can get a signature of this winding number. I'll give you details about how that happens in a second. So I'm going to use, how are we doing for time? Left, okay. So I'm going to use a one-dimensional Hamiltonian. That's theoretically the simplest one. There are experimental groups that are approaching this one-dimensional limit. But even beyond that, there have been experiments which are not truly in the one-dimensional limit, but have been modeled quantitatively using one-dimensional theories. Okay, so the basic features of the one-dimensional treatment stay when you have radial or axial degrees of freedom, but additional features come in. So with that justification, I'm just going to use a one-dimensional Hamiltonian. The reason there is an integral in the Hamiltonian is because it's a many-body Hamiltonian. So we are trying to sum the energies of all the atoms on this ring, but each atom is delocalized along the ring. So we have to integrate around the ring on the angular variable. So this is just the rotational kinetic energy of the atoms. I is the moment of inertia of each atom about the ring center. This is the interaction of the optical lattice with the atoms. This includes binary collisions between the atoms in the condensate. This is the energy of the electromagnetic mode in the cavity. And this is the external driving laser. So we are writing this Hamiltonian in the frame of the frequency of the driving laser. Now going back to the physical picture that I gave you, I am going to write a guess for the atomic wave function, which consists of the original persistent current and these 2 side modes. So these are all plane waves, and these C quantities are bosonic operators. And if we normalize to the number of atoms, then that just means that the number of atoms in the original persistent current plus the number of atoms that go into the 2 side modes have to all add up to the number of atoms that we started with. Now, the number of atoms that go into the side modes is actually very small, much less than 1%. And so the number of atoms in the original persistent current, which in our simulations is about 10 to the 4, is much larger. And so we do not expect the dynamics of this mode to be dominated by quantum fluctuations. Okay, it's going to be basically, essentially a classical dynamics. So we go to the mean field approximation, we just treat this to be a complex number, and the real quantum dynamics comes from these two side modes that are created in the condensate. So if you pack all these things together, then you get a Hamiltonian, which looks very much like the canonical Hamiltonian of cavity optomechanics, because you have not one, but two mechanical oscillators, and their coupling is to the photon number inside the cavity via the displacement. But now this is the displacement of the bosonic modes of the condensate, and then you have the driving term, and this term is due to collisions. So I will first give you a simple analysis by neglecting the collisional term, but for the full numerical results, I will include it and show you it makes essentially no difference. Now, the interesting thing, of course, is that the mechanical frequency corresponding to these two side modes contains the parameter that we're after. We would like to find this winding number, that's our task, and that is contained inside this mechanical frequency. So I ignore the collisions, this is my Hamiltonian, I write the equations of motion, and now I bring in the fact that we are not really in a zero temperature system, so there is some loss and there is some noise, and that is done using the standard formalism of quantum Langevin equations. And that gives us basically equations for the two side modes in terms of two damped driven harmonic oscillators. So this is one side mode being damped at a rate, which is basically the rate of decay of persistent current, so that's minutes. And then this is the mechanical frequency squared. This is the driving due to the radiation pressure in the cavity. And this is the noise fluctuation. So we are assuming white noise. This is just delta correlated. Same thing for the other side mode. And this is the equation for the field. And now I will ignore damping for a second because persistent currents are really long-lived. I will ignore radiation pressure driving because the number of photons is very small. I will ignore noise. And then I just have a simple harmonic oscillator oscillating at frequency omega c. And likewise this for omega d. And if I put those dependencies in here, I immediately see that the field is modulated at omega c and omega d. And what that means is that the transmission through the cavity should have two peaks at those frequencies, and from them we can recover LP. Okay, so that was the hand-waving argument. I will now go to more numerical approach. So these are some of the parameters. It's not a complete list. There's actually a whole bunch of parameters because the atomic superfluid problem brings its own parameters and the cavity optomechanics brings its own parameters. So and there is actually a sort of like a double feature here. But this is roughly the number of atoms. Like I said, 10 to the 4. This is the radius of the ring. These kinds of rings have been made already. We are looking at low winding numbers for now. The cavity finesse is not too demanding, and so on. This is a follow-up article. Actually, I just got the reviews back from the referees this morning, and they look pretty positive. So we are going to hopefully publish that. So the beam waist. So the beam waist is actually depends on the orbital angular. It's a constant times a function of the orbital angular momentum. And so since we vary the beam waist, we adjust the since we vary L, we adjust the beam waist so that it is always overlapping with the ring of the BC. So it's a few tens of microns. That's what you're asking. Is the detuning of the light probing the cavity from the atomic transition. No, the ring trap is magnetic. No, the ring trap is magnetic. It's not optical.
Oh, it's not optical.
No.
So this is what light? I mean, this.
This is the light that is probing the atoms in the cavity. Far off resonance.
Far off resonance.
Okay, so that the spontaneous emission rate is negligible during the experiment.
Okay.
You can have optical traps which are ring traps, but that will complicate the dynamics very much. So we decided to go with magnetic traps. Okay, so we can look at the steady state solutions of the system, and because it's the optomechanical Hamiltonian, we expect to see standard optomechanical phenomena. So here we're looking at the number of photons inside the cavity as a function of input power, and for large enough power, we see bistable solutions. And the interesting thing, of course, is that this happens at very low photon numbers. 15 or 20, So typically bistability is said to be a phenomenon which you see for very high photon number, but in these systems, light matter coupling is so strong that you see bistability at very low photon numbers. In fact, in the ETH experiment, they see bistability at 0.2 average photon number inside the cavity, okay? And so this is a plot that shows how, for various kinds of optomechanical systems, the coupling between light and matter, which is the coherent coupling, relative to the dissipation in the system, this is a quantitative term called the cooperativity, goes. And actually, the cold atom systems are right up here. So they can have cooperativities of about 10 to the 4. And that's why optomechanical phenomena occur at very low powers. So I should have said the solid lines correspond to the collisionless model and the dotted lines correspond to the inclusion of atomic interactions. You can see the difference is not much. Okay, so we can look at what's coming out of the cavity by calculating the linear response of the system, and the appropriate thing to look at is the phase quadrature. And if we plot that as a function of frequency, sure enough, we see the two peaks. So this is without collisions, and this is with collisions. And we have verified that you can recover the winding number from either one of them. A nice combination to look at is their difference, because it just goes as this particular combination of parameters. And in the experiment, you know the moment of inertia and the optical angular momentum, so you can get LP. If you plot the same quantity as a function of input power, you get the noise budget for the measurement. So there is short noise, which goes down with power. There is radiation pressure back action noise, because the more power you use, the more you disturb the condensate. Then there are some finite temperature effects. So there's, of course, the intrinsic uncertainty, quantum uncertainty of the bosonic mode, and everything put together gives you this total noise, which is minimized at the standard quantum limit. We can calculate the sensitivity of the measurement, and we find that the time taken for the measurement is much smaller than the duration of a persistent current, so it's almost in real time. The sensitivities are very low. It's 1,000 times more sensitive than anything that's been demonstrated. The number of atoms is in the side modes is much, much less than 1% actually. So the measurement is not a quantum non-demolition measurement. It's a minimally disturbing measurement. It's certainly not killing the entire condensate. And we can go through, we have made sure that the system parameters have been chosen, so everything is stable. And we confirm that there's this linear response regime in which we can have a faithful measurement. And then if you use too much power to drive the cavity, the lattice becomes deep and it stops the atoms from rotating, and then the fidelity of the measurement goes down. So far, everything I have said is about a kind of passive measurement. The condensate is rotating, the cavity comes along, makes a measurement. But actually, like I told you, optomechanics is a toolbox for not only measuring, but manipulating mechanical motion. So here is a very small calculation which shows how radiation pressure can entangle these two rotating currents, these two rotating matter waves. And this is just the bipartite entanglement, which shows a kind of threshold. You have to use enough optical angular momentum to create the coherent coupling. And then if you increase temperature, of course, eventually entanglement vanishes. So to conclude, we have theoretically shown that using some ideas from optomechanics, we can provide a solution to this measurement problem. But actually, you can do lots of other things. You can make a memory for photons that carry orbital angular momentum. People try to use these for quantum communications. And so far, the best memory times are like 400 microseconds, and these are in atomic vapors. But if you use the fact that these supercurrents rotate for so long, you can make a nice memory for photons carrying orbital angular momentum. The nice thing about this is that people already know how to store and retrieve photons from mechanical elements oscillating in cavities. So this is well known in standard cavity optomechanics and other things. So basically, this is a coherent and reversible interface between atomics, between optics and atomic superfluid rotation. I should mention, I said I was looking for postdocs. I put my email down there in case I forgot to mention. Anyway, thanks for your attention.
So thank you, Mishkatul, for nice talk. So nice talk.
I'm sorry?
N is equal to 8 for bipartite entanglement just now. So why this threshold is required? L is equal to 8.
So the way I like to think about it is that when the atoms are going around, they are basically interacting strongly with the light at these points, at the maxima. And the number of maxima goes as 2L. So the larger L is, the more often atoms get to see that strong interaction, so there is enough coherence in the system to beat all the noise and the temperature effects to create
It
entanglement.
will be bipartite and multipartite entanglement. That's what I was wondering.
So there is multipartite also. I have not shown. We have calculated tripartite entanglement between the light and the two modes, but we can trace the light out and get the bipartite also.
Okay, fine. And another question, we have so many applications for orbital angular momentum of light, and you have got this orbital momentum for BEC since long time, like maybe now 15, 20 years around. But I don't see applications coming out of atom interferometry is well-known technique now that's being used. So if there is any application, it has come out of OM in atomic system.
Yes, yes. So part of this is, of course, the nice fact that photons don't interact much with anything. So you can transmit them. You can transmit Laguerre-Gaussian modes through media like Tarak does, through turbulent atmosphere, and so BEC is much more fragile. You have to put it under vacuum and things like that. So I think I'm not qualified really to comment on the technical aspects, but I do know that from questions people have asked me before, that they were waiting for experiments which really build nice waveguides for these atoms, and now they are available. So the von Klitzing experiment that I mentioned is smooth to picokelvin for a 10 nanokelvin BEC. So that's really smooth, and you can get atomic. So now you can think about doing multiple orbits and interferometry, and those things will become possible. The other thing is, I think, and this is the way in which we are trying to sell this work, is that without using cavities, the limitations of just using ring BECs are too much. But now you have this established paradigm, it's almost immediately clear how to make a useful memory, which is 5 orders of magnitude better than anything that exists. And it's within technical reach. So we are hoping that this direction for atomtronics will help.
Hello.
Okay. So I have a question. So in a BC, there is always a mean field interaction. So what is the role of this mean field interaction in the entanglement you're going to create? Is it going to help in the creation of the entanglement?
So the effects are shown right here. The solid curve is without the mean field effect, no collisions. And the dot dashed curves are with the mean field effects taken into account. You see there's not much difference, at least for the parameters we have taken into.
Hello. Yeah.
Driving cavity with plus minus L, and cavity has L equal to 0, and you are creating standing waves. Am I right?
So standing waves with L not equal to 0. So with plus 2 h bar and minus 2 h bar.
But then this cavity should support.
They do, yeah. These are people experimentally have shown that these lattices can be produced within Fabry-Perot cavities. They're just like the interference of higher order modes. You don't need a fundamental mode.
So cavity should be a 3-mode.
No, just this single mode, which is a superposition of the plus minus L. These are transverse modes.
Yeah.
But these are also cavity modes. So,
It's creating in this direction.
so there will be a lattice in the Z direction also.
That is due to the resonator modes, right?
Yes. So if you write the intensity, it will be cosine square kz, cosine square L phi. And now we are assuming that the BEC thickness along the axial direction is much smaller than the optical wavelength.
Okay.
So that momentum transfer along the axis is negligible.
Last question, sir.
So, as you have said that this BEC is trapped between the magnetic trap, but when you are choosing the Hamiltonian, in that case, you have chosen on optical lattice, right?
Optical lattice is probing the BEC.
Yeah, and actually this optical lattice is related to the angular momentum, orbital angular momentum L.
Yes.
So how does it affect the system, or like it is how it is coming to the system?
So the idea of the lattice is to probe the rotation of the condensate, causing as little disturbance as possible. Okay, so I told you that we see bistability at 10 photons on average inside the cavity, but actually we operate far below that limit. So we are somewhere here, where you can look at the number of average photons. It's less than 1. So this lattice is very weak.
Okay.
Okay, and the only effect of that lattice is to give us in the transmission peaks which are resolvable above the noise in the system. And as long as we see those peaks, we don't really care what the lattice is doing.
Okay.
I'm sorry, which one? I'm sorry? How much time scale? Time scale we have not really looked at. So if you want to use it as switch. Yeah, so most studies that I know of bistability in these systems sort of climb slowly with respect to all the other time scales, and then see the hysteresis curve as they trace it out. I have not seen anything that goes fast and or analyzes how fast the time scales are. Fast or slow, that's what I want. Yeah, I don't know. I would have to calculate it. Yeah.
Maybe we can continue in the break.
Yeah.
So,
Sorry, go ahead.
let's thank once again Mishkatul for very nice talk.